Hello class, we're back. So we're going to continue on with KP, KC, right? So we're going to do sample exercise 15.2, converting between KC and KP. This is on page 618. So we're going to have this reaction, which is actually called the Haber process. Not that that really matters. N2 gas plus 3H2 gas goes reversibly between 2 NH3 gas. All right. KC at 300 degrees Celsius is 9.60. Uh, 300 degrees Celsius. So, and then the question asks, what is KP? Okay, so we're going to use our equation that I just wrote on the board, and for some reason I can't remember off the top of my head. We're simply going to use KP equals KC times RT delta N. Okay? Again, R is the gas constant, 0.08206 liters atmospheres divided by mole Kelvin. T is the temperature in Kelvin. KC is given, so you just got to plug in the numbers, right? So we have, whoops, 9.60, you can write it. Again, no units on KC, right? There's also no units on KP. Actually, I'm going to use a brackets here because that has to be raised to the delta N, right? Moles of gaseous product minus moles of gaseous reactant. The temperature 300 at 273.15 because we want Kelvin. Close my brackets. Again, delta N is the number of moles of gaseous product minus moles of gaseous reactant. So here we have 2, right? 2 moles. What do we have over here? We have 3 plus 1, 4. So 2 minus 4. That's going to give us -2. Okay? What does the negative sign mean? That means it's going to move down to the denominator. If I write this out, which I will, we're going to divide it by that squared is what's going to happen. That's what the -2 is going to mean. Times by 573.15 Kelvin. And then that is squared. Okay? So plug that into your calculator. Make sure you get this order of operations correct. All right? And according to our book, we get a mighty 4.34 times 10 to the -3 for our KP. Again, no units. No units on KC or KP. It's supposed to be a capital K. All right? So that was pretty straightforward. I mean, we just had to plug in the numbers, right? Again, remember, on your test, delta N, moles of gaseous product minus reactant, right? I'm not going to give you the equation, but I'm not going to tell you what that is. You have to remember. Let's take a look at the practice exercise to accompany that, right? This one, we're going to solve for KC instead, I think. Hold on one second. All right, so the practice exercise 15.2. We're going to look at this. we're gonna have 2 SO3 gas goes reversibly to 2 SO2. Wait, is that right? Wait, what? Uh, 2 SO2 gas plus O2 gas. They tell us Kc is 4.08 times 10 to the minus 3 at a temperature of 1000 Kelvin. Tell us temperature 1000 Kelvin. And they ask, what is Kp? Right? So again, we're going to take this equation, and why on earth I cannot remember it. Ah, wait, this one's the same. I wanted one that was different. Oh, man. This one's pretty much the same as we just did. Sorry, I want to do a slightly different one. Well, I'll finish this one first. Again, it's basically plug and chug, okay? Yeah, freaking very straightforward, actually. And actually, I'm not going to go ahead and do this, all right? You can calculate it out, right? Again, what would delta N for this one be? Again, moles of gaseous product minus moles of gaseous reactant. So in this case, our delta N is equal to 3 minus 1. It's going to be 2, right? So this will just simply be squared, right? You can plug the numbers in and check it out, right? It is basically 0.335. Sorry, I want to do one the other way though. Let me look in the back of the book. Oh, come on now. Ah, come on now. Give me a freaking break here. Actually, we'll do 15.34, all right? That's what we'll do. All right, 15.34. So we're going to have this equation. Two hydroiodic gas is going to go to H2 gas plus I2 gas. Okay? Then they tell us at equilibrium, they give us the equilibrium. Well, once again, I cannot believe this. I am picked the wrong bloody problem once again. But we'll do this one anyway. They give us the equilibrium concentrations and they ask us what is Kc. Okay? So we'll calculate this out, right? HI equals 3.53 times 10 to the minus 3 molarity, equilibrium concentration. Then we're going to have H2 concentration equals 4.79 times 10 to the minus 4. And we have the I2 concentration equals 4.79 times 10 to the minus 4. Molarity, right? So we want to know Kc. right? Well, pretty straightforward, you plug it in, right? Write out the expression for Kc, products over reactants, right? Concentration of H2 raised to its stoichiometric coefficient, which is 1, times concentration of I2 raised to its stoichiometric coefficient, which is also 1, divided by concentration of Hi squared, right? Now plug in your values. So H2, 4.79 times 10 to the minus 4 molarity, times concentration of I2, which is 4.79, times 10 to the minus 4 molarity, which will basically be 4.79 times 10 to the minus 4 squared, anyway, divided by the squared concentration of Hi, and remember, units don't matter, okay? And I gotta enter in this junky calculator here. This is gonna take a minute. Yeah. 0.79 times 10 raised to the minus 4. Close that parentheses. I'm gonna square that. Enter. Divided by that. Gonna put let's see here, I don't want to do this. I'm gonna do double parentheses. 3.53 times 10 to the minus, whoops, it's 10 raised to the minus 3. And hopefully I entered that all incorrectly. And if I did, I'm getting Kc is 0.0184. Remember, no units, right? 3 sig figs, no units. Pretty straightforward. All you have to do is plug the numbers in, right? Any questions? Email me. We will do another one. Let me make sure I picked the right problem this time. Oh, come on. All right, 1536. By the way, I've always had a problem like that one on the test. So, yeah, so know how to do that, right? Let's take a look at 1536. Again, what do we have here? Oh, man. We're going to have PCl3 gas plus CO2 gas is going to go reversibly to PCl5 gas. Okay? They tell us that the temperature is 450 Kelvin. Sorry, it's supposed to be capital K. And let's see here. And then they give us equilibrium partial pressures. So we're going to have, oh, there went my timer. So we're going to have PCl3 is going to equal 0.124 atmospheres. PCl2 is going to equal 0.157 atmospheres. And PCl3, or 5, sorry, PCl5, oh, I'm messing up here. It's supposed to be a little P on there, right? PCl3, partial pressure PCl3, partial pressure Cl2, partial pressure PCl5. At equilibrium, this is 1.30 atmospheres. And sorry, after all that, what's it asking for? It's asking for Kp. So So we're gonna write out the expression and plug the numbers in. Again, Kp, products over reactants, okay? Partial pressure, PCl5 raised to a stoichiometric coefficient, which is 1, divided by reactants, partial pressure of PCl3 raised to a stoichiometric coefficient, which is also 1. Yep, come on, give me a break. Come on. Sorry about that. Partial pressure of Cl2 raised to a stoichiometric coefficient, right? And then simply plug in your numbers, okay? Partial pressure at equilibrium, we end up with 1.30 atmospheres divided by 0.124 atmospheres times our 0.157 atmospheres. All right, plug all that in. Let's see what we get. 1.3 divided by 1.24 divided by 1.57. Hopefully I got that all in there correctly. Hit enter. If I do, I'm getting 0.668, right? Again, no units, no units, okay? Now, let's add another part to this question. Where's my sheet? Let's ask, what is Kc? Okay, so that's the first part, okay? That's the first part, Kp. Now we're gonna ask, what is Kc for this reaction, okay? So I'm gonna have to erase some of this to make some room here. We're gonna ask, it's part B, okay? Part B, what is Kc? I'm gonna erase some of this. Now we want to know